Now we will learn about acids and bases. Acid base chemistry is one of the most important aspects of studying chemistry. If you were to take higher levels of chemistry, you would see how deeply is this subject matter studied. Now, acids and bases, simply by their physical properties, we can identify them as compounds, acids as compounds which taste sour and they dissolve some metals. They also can cause plant dye to change color. You know that acids taste sour because you may be aware that many fruits are sour, and especially when they are not ripe they are sour because mostly they are still, their content is mostly acidic, but over time as it ripens it turns into sugars and it turns sweeter. Similarly, there are lots of vegetables that also contain acids. Acids can dissolve metals, and when they dissolve metals they release hydrogen gas. We never pour down strong concentrated acid down the drain because it can dissolve the pipes. And the last part is what becomes the basis of something known as litmus test, which we'll look at later. Bases, on the other hand, taste bitter. Many of the medicines contain bases in them. And if you had ever had to take some strong medication for that was you had to take some strong medication orally for some condition, you may regret having taken it because of the taste. Well, if it tastes bitter, the chances are it's because it's basic or made up of bases. They are slippery and they are corrosive. Okay, so these are the two physical distinctions between acids and bases. But what about their chemistry? Chemically, there are two theories by which we classify acids and bases. The first one is called the Arrhenius theory, which is named after a Swedish chemist in the early 1800s who gave us his idea of acid and bases. And the second is known as the Bronsted-Lowry theory, after the two scientists who worked in the early 1900s and gave us their definitions of acids and bases. So we'll look at the first one, the Arrhenius theory, and see what the definitions say. Oops. So according to the Arrhenius theory of acids and bases, an acid is a compound which when you dissolve it in water, it disassociates to produce hydrogen ions. Here is the hydrogen ion. So HCl is an acid. It's called hydrochloric acid. When it's dissolved in water, we write down AQ and it produces H plus and Cl minus. We ignored the chloride ion part. It's this part by which we classify it as an acid. Many of the acid compounds have their chemical formulas begin with the H, which ultimately ends up being dissociated, but not all the time, as we will see. Now, H plus is also called a proton because if you recall, a hydrogen atom has a proton in it and an electron. Hydrogen does not, well, one of the main isotopes of hydrogen does not have a neutron, just has a proton and an electron. And if an electron is gone, we have H plus, but what's remaining is just a proton. So when we talk about hydrogen ion, it's the same thing as a proton, and we can use those two words interchangeably. So an acid is a compound which disassociates to produce hydrogen ions or protons. Base is a compound which when dissolved in water disassociates to give us hydroxide ions. So these are the two definitions for acids and bases, the Arrhenius definitions of acids and bases. They are very straightforward and they are very easy to memorize. However, there was a problem with the Arrhenius theory of the early 1800s in that there were many compounds which have the properties of bases like ammonia, but they do not dissociate to give you hydroxide, OH minus. For example, ammonia, if you were to dissolve it in water, how would it disassociate to give you OH minus? There is no OH minus, there is no oxygen here. And yet it had the properties of bases as we understood them, the chemical properties. Many other properties of acids and bases exist beyond their physical properties of taste and touch and so on. And according to those properties, ammonia should be a base, and yet it's not going to dissociate to give you hydroxide. So how do you classify ammonia as a base if it is acting like a base in chemical sense? That's when the Bronsted-Lowry theory, which was developed in the early 1900s, comes to our aid. According to that, an acid is a proton or H plus donor. Now, be very careful with the wording here. Again, H plus is involved when it comes to an acid, even in the Bronsted-Lowry theory. But the word here, the key word here is donor, meaning that that H plus is being given up to somebody. It's being donated to somebody or something. In the case of the Arrhenius theory of an acid, an acid is a substance which just dissociates to produce H plus or a proton or a hydrogen ion. So it's just being produced. We do not care whether it's being donated to somebody or not. So when an HCl dissociates and you get H plus, that's an acid. It's just being produced here. But all Arrhenius acids are also Bronsted acids. The reason is when this H plus is being produced, it is ultimately going to be donated to some chemical species in solution. So whether it's an Arrhenius definition or Bronsted definition, the wording is different, but all Arrhenius acids can be classified as Bronsted acids. And what about the definition of a base? A base, according to Bronsted-Lowry theory, is a substance that accepts a proton. And that's where all the difference lies. No more is a base, according to Bronsted-Lowry theory, a substance which dissociates to give you OH minus. It doesn't have to do that. But rather, a base is a substance that accepts an H plus. As long as a substance is going to accept an H plus, it's a base. It turns out that all Arrhenius bases can be classified as Bronsted-Lowry bases, but not all Bronsted-Lowry bases can be classified as Arrhenius bases. For example, ammonia is only a Bronsted-Lowry base, but it's not an Arrhenius base because it doesn't have OH minus in it. However, compounds like NaOH can be classified as Bronsted bases because when you dissolve this in water, OH minus will accept H plus, as we will later see, and so it can be classified, and it is classified as a Bronsted base. So here is a Bronsted-Lowry reaction between an acid and a base. Now notice what's happening. We are taking an acid HCl, and like I said, all Arrhenius acids are classified as Bronsted-Lowry acids as well, whether it's donating a proton or just disassociating to give you H plus, it's the same thing in the solution. HCl, when it disassociates, it will give you H plus. However, in water, what will happen to that H plus? It will get donated to H2O, forming H3O plus on the right side. So here, HCl is acting as an acid, a Bronsted-Lowry acid or an Arrhenius acid. Water, on the other hand, is acting as a Bronsted-Lowry base. Why? Because it is accepting an H plus. It's not acting as a Arrhenius base, but a Bronsted-Lowry base here. So here is where you see the two definitions in action. And here is what you classify as a Bronsted-Lowry acid-base reaction. Here is another reaction, and this is also a Bronsted-Lowry acid-base reaction. But now notice what ammonia is doing. Ammonia on the right side is turning into NH4 plus. How did that happen? It must have accepted an H plus from somebody. If it's accepting an H plus, it's acting as a base. This is why it's basic. And what is acid doing here? What is water doing here rather? Water is donating that H plus that ammonia wants, turning into OH minus. This is why water is acting as an acid here. So again we have a Bronsted-Lowry acid-base reaction where we have an acid and a base, but in this case water is the acid, while in the previous case water was a base. When it comes to Bronsted-Lowry definitions, things like this will happen a lot, where a compound can act as an acid in one reaction and can act as a base in another reaction. Water is a special compound in that sense, which has the properties of an acid as well as a base, and it's called amphiprotic for this reason, where it can act as both, and it's commonly used as a solvent for other acids and bases as well. So starting in the next video, we will see more details concerning the Bronsted-Lowry acid-base reactions. And one thing to notice here in this reaction is this reversible arrow, which will come to again later.